how many valence electrons are in zinc? So, valence electrons in zinc. To be able to find this answer, we actually need to use our electron configuration, especially because zinc is a transition metal. It's hard to just see it and be like, okay, well, zinc then has, exactly, what does it mean for zinc to be in the 12th column? What does that mean for electrons? This is why I do stress that if you're ever unsure, it does, no matter where you are in the periodic table, if you know how to do your electron configuration, that's usually the best approach to figure out how many valence electrons you're working with typically, especially when you're dealing with transition metals. The alkali and alkaline earth metals, those ones can kind of be seen as face value, and also between columns 13 through 18, those ones you can kind of assume what their valence electrons will be. But for transition metals, this is when we just do our check through our electron configuration. So with that being said, we have to make sure we write our subshells in properly. We have 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f. Okay, and it keeps going, but this is as far as I'll go, just because we are trying to get to zinc. Okay, so zinc, right, is the 30th element on a periodic table. So let's actually, what I like to do, especially if you're having a hard time with electron configuration, the goal is to count through. The S subshell can only fit 2 electrons, okay? So that'll be the first and second, elements in your row of that periodic table. In this case, it would be hydrogen and helium. That'll be 1 and 2. So right now we have this completed, and we have at least one S2, okay? And then we follow that trend. Lithium and beryllium would be what compose that 2s section, and we completely go past that because we're aiming to get all the way to 30, okay? So 2s2 is complete. And then from boron to neon, that would be your P subshell, and you notice that there's 6 elements in that span. So we'd count through P, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6 for the neon. So these now we know we have 2p6, and we keep going forward. Okay, we're in the third third row right now. So now we've gone past that into the 3s. So that's 3s2, and then we have aluminum through argon. That would be the 3p6, and now we've passed that. And now here we have, okay, 4, where do we go? Just make sure, yep, 4s2, potassium and calcium, okay? So we've gone past that. But now we're actually going all the way towards zinc. Now we've entered, as you can see here, based on these arrows, we're entering our D subshell, okay? And the D subshell works a little bit different if you notice. Instead of it being that we say 4D, this subshell here on the 4th row actually starts with whatever row you have minus 1. So it would be 3D actually, okay? So in a sense, think of it being actually in the orbital prior. So we have from scandium all the way to zinc, and if you count, that's 10. So that's 3D10, okay? And now what I like to do is rearrange it based on the numbers that come first in front of it. So it's 1s2, 2s2, 2p6, 3s2, 3p6, whoops, almost did it again, 3d10, 4s2. It just allows for a better visualization. And you can actually check that you actually ended up on the 30th element by adding up all these superscripts. So 2, 2, 6, 2, 6, 10, 2. So let's see what happens when we do that. 2 plus 2 plus 6 plus 2 plus 6 plus 10 plus 2. And it does indeed equal 30. So this actually would be the electron configuration for zinc. So now it's asking for its valence electrons. As I said, we have now from 1 to 3. That would be your shell prior, because the 4th is now the biggest numbers. That'll be your most outer shell. So with that being said, we only count this as your valence orbital, okay? And to find out how many electrons, we look at the superscript there, okay? And that's 2. So for this question, the valence electrons in zinc actually would just be 2 valence electrons, because that would be what is available from that most outer orbital, okay? So that would be the valence electron for zinc. Just to be able to write this easier, because as you notice, if you get further and further down the periodic table, it can get quite extensive. So what I also like to do is that if we look at the most previous noble gas, which is argon, okay, we can start from there, and you notice that we now just hop right into our 4s2 and the 3d10. And as I said, I like to just make sure that the 3 comes before the 4, so it'll be 3d10 4s2. And this is actually the same thing as that, okay? It's just a noble gas short-handed configuration. And I just do this as well because it does allow me to have an easier time visualizing my outer shell. Although we still have the 3 here, the important thing is that we recognize that this 4 is going to be in the shell that comes after, okay? So yes, 2 valence electrons. As you can see here, they did that as well. They actually provided both the short-handed and the long notation. And the goal here, the final energy level, 4s2, dictates that the number of valence electrons in this case is 2 electrons. So this is correct. So now we move on to question 6.